Okay, we're going to get started. So we have a celebrity in our midst. If you ever go to New York City and you know Python, you will know James Powell. James Powell runs the New York City meetup. I think he always says it's the second largest. It's the largest now, the largest Python meetup in the United States. He also happens to be a wizard. This man is a wizard of Python. I thought I know Python pretty well, but every talk I go to of his, I am completely blown away by the intricacies of how well he knows the language. So today, we're learning about generators, and generators will free your mind. Let's welcome James Powell, everyone.
Hi, everyone. My name is James. I've given generator talks at the last few PyData events, most recently in London in February. And I thought for Silicon Valley, I would give a different talk based on the same material. So today, I'm going to be showing you how generators can free your mind, how they can fundamentally change the way you think about the code that you write. The slides for this talk are on GitHub. So they're on a gist. If you look at the gist URL, it's way too long for you to type in there. So just go to gist.github.com, DUTC. It's the very first one right here. You can see this is a talk that I gave a couple days ago. Just as a brief introduction, or just some information on how to contact me. If you have any questions about this talk, you can email me. I have the domain don'tusethiscode.com. I consider it to be a disclaimer for every piece of code and every presentation that I give. So trust me, I believe in this material, but don't use this code. On Twitter, I'm also don't use this code. And I have a blog, which I need to update a little bit more at seriously.don'tusethiscode.com. You know, I'm really driving at this. If you're on IRC, I am DUTC on IRC, and I camp on Freenode on NYC Python on Freenode and on the Python channel on Freenode. Sometimes you may see me referred to as Dutch, because people will misspell DUTC. I'm from Texas, and that stands for don't use this code, Haas. I got some jokes in this presentation. I'm trying to bring up the energy level a little bit. So as Matthew said, I run NYC Python. NYC Python is the world's largest Python meetup group. I'm going to click here and show you. There you go. This is my meetup group. We have almost 5,000 members. It's probably the most active technical community in New York City. You can see we have events scheduled out to August already. And we regularly have events with hundreds of people. 120 people were there at a utilities talk a couple days ago. Additionally, NYC Python is running a Python conference in August on the 15th and 16th in New York City called PyGotham. The CFP will be out very shortly. This is going to be an amazing event. We held PyGotham in 2012 and 2013, and it was awesome. I think PyGotham was the first conference at which I ever spoke. So I feel very close to it. Also, this past March, I ran a conference for finance professionals called For Python Quants. It was a one-day event. 200 people were there. It was really amazing. We had some really fantastic speakers, including some PyData regulars like Ben Lerner and Dr. Eve Hilpish come and speak. It was a really, really cool event, and we're thinking of holding this again in New York at the end of Q3. Additionally, I thought just to warm up the crowd, I would add in a joke. I have a list of jokes on my computer, and I thought this was the funniest and most appropriate. So I'll tell you that I come from a very troubled background. I used to be addicted to the hokey pokey, but I turned myself around. It's a tough crowd today. So, broadly, the themes of this talk are showing you how generators can be a useful way of modeling problems in Python, how to fundamentally change the way that you model or think about your code. What this talk is not about is what a generator is. If you're curious what a generator or coroutine is, look at my previous presentations. I've given talks on that in PyData London, in Silicon Valley last year at PyData New York. There's a lot of material there. And I would say that for sake of time, I have chosen not to cover it. Additionally, one of the reasons that people reach for generators, I think, is out of a desire for either time efficiency or memory efficiency. They want their code to run faster or use less memory or use memory in a more deterministic fashion or a more predictable fashion. I won't be covering this today, although it is a very important topic. I think, however, that the way that generators allow us to change the way that we write our code is far more important than both of these things. Additionally, for this talk, all of this is in IPython notebook. I have a couple of future imports. So if you're playing along, this is a little bit of pretext for the code that we're about to see. So I want to start this presentation with what I think is a very good analogy to how we should think about generators, which is to first think about functional programming. When we first ran into functional programming, it changed the way that we thought about the code that we wrote. And I think for many of us, functional programming has already freed our minds. So I'll give you an example of that. Let's say that we have some report. We have some business that has branches in the US and UK, in Central America, and they have a branch in Antarctica, but it doesn't make any money. And like most businesses, the amount of money it makes in each region is some random number between about -$4 million and $4 million. And somebody asked us to write a report to send this to some high-level executive. So they said, I just want to print out how much money I made in each region. And so you can see I have a really simple piece of code here. I just iterate through them, and I print them out to the screen. But as we know, this is never enough. So somebody says, actually, that really looked ugly, and I couldn't read it on my BlackBerry. I want to read this a little bit more easily. So you go in there, and you figure out what's the maximum region that I have, and how much do I have to pad things over, and you get the columns nicely aligned. And people are happy for about 3 minutes. And they go to you, and they say, well, you know, in addition to printing this out of the console, I also want to write it to a file. And you may protest, but they insist, and you decide, OK, I'm going to write it to a file. So I'll add another parameter to this function, and it'll be called file name. And if you provide a file name, I'll use a context manager, I'll open a file, and I'll write all these lines to a file. And you can see the output hasn't changed, but now it can be written to a file if you give it that parameter. But people still aren't happy. They say, we also want to write it to a log. So I'll use the logging module that's built into Python, and if you give a parameter called toLog, true or false, it'll also write it to a log. And you can see the function begins to grow. And this is the natural progression of many of the functions, many of the pieces of code that we write. People ask for requirements, and we start to encode them, additional modalities and knobs, and all these buttons into our functions. And then somebody says, you know, I'm used to seeing numbers in Excel, and this is still not enough. I want to have the option to have an accounting format where my numbers have parentheses around them. So you add that in there as well. And you can see at the very top, I have a accounting equals false. And if you set the accounting format, it'll do the nice commas, and it'll put parentheses around negative numbers. And it makes somebody happy for a short period of time. But then they say, you know, we also want this to be emailed out. And the one thing that's different about emailing it, as opposed to logging it or writing to a file, is that you need to construct the entire email body at once. Because your email function takes a subject, it takes a to list, a CC list, and the entire body. So now you have to write another piece of code out there that collects all the lines that are created and then emails them to somebody else. And you can see that we've all seen code like this. It gets progressively more absurd as it goes along. And all of this functionality starts to be subsumed by this single function. This function has grown so big, it can't even fit on the screen, or the output can't even fit on the screen. And so I don't want you to look at this. This is really ugly. So we think, how can we do this better? And we reach for something like functional programming, just very basic functional programming approaches. And we see that it can immediately improve the code that we write. Now, I had to include this because this is part of the next piece. This is why you should never use my code, because I wrote this in earnest for actual use. Don't worry about what it does, because you'll see in the next slide. But I just wanted to put that up there. It's really, look how awful that is. There's a meta class. There's an inline meta class in here. And it's, oh my goodness. Don't use this code. So what we say to ourselves is what we see here is we have some, instead of having this true-false value that toggles these different modes, instead we'll inject that functionality into the function itself by passing a function. And that function will be called write. You can see it's right here. It's called write. And you can see the template for the line will also be injected as well. There'll be a function called template that'll take the pieces of data, and it'll template the line. And you can see it's just using basic advanced string formatting. And there it is. And we took something that was this long, and now we have the ability to add in all of that functionality that we had before, plus more, in smaller code, in such a way that we can add additional functionality. Like we can write to 2 logs at once without changing that original function. We've fundamentally simplified the code that we've written while making it more powerful for people to use. Additionally, you can see we've added one nice little feature, which is for the line that's 0, you have this little Excel accounting format where it puts a dash instead of a 0. So what does this example show us? it shows us that functional programming can free our minds from some presumptions about modalities. We don't have to worry about encoding all these different modes in our code. We don't have to have a bunch of true-false arguments at the top and then all these if-else blocks switching between all the different modes we have. We can actually inject that functionality directly into the code that we write by passing functions in. You could think that if you wanted to write that data to a database, you would just write in that writer function, you just create your own little custom writer function, and you'd write a db.con.open whatever, and then just an insert statement, and you'd be done. Additionally, functional programming has substantially simplified our API. If you look at the code that we have, you can see that the API is very simple. We have a list of markets that we take, and that's what we iterate over. We have a function called write that defaults to just a print function, just print it out to the screen, but we can replace it with something to print to logs, to write to a database, to write an email, whatever we want. We also have a template function that just takes the data and templates it into a line to allow people to see Excel accounting format if they want, or a decimalized format if they want. So we've fundamentally simplified our API. And it has furthermore empowered our users. So people who see our code, not the end users of our code, but the other programmers we have to work with, are now empowered. They can do a lot more with the code that we've written without having to worry about all the presumptions we've made. Now, there is one interesting thing, especially on the API example, which is in this version, the API is both simpler but also more precise. Namely, for writing the output, you can only pass a function that can write the output line by line. So in the email example, you have to have the entire body. May not be possible with this particular API. So we've both simplified the API, but also made it more precise, a little bit more restrictive. Now, one thing that I'm sure a lot of you in the audience who've touched languages like Haskell have seen is that pure functional programming can further free our mind. I don't want to go into this too deeply, but you could even say that in the pure functional world, we wouldn't even bother to handle any output whatsoever. And honestly, all it should do is write to the console, and then we'll have some command line app that pipes it to wherever it wants to go. OK, maybe. What I do want to say, though, is that when we talk about functional programming, Python is not exactly it's not a language that sells itself on being a functional programming language. If you talk to the core developers, they'll often tell you that they believe that an iterative approach is, or rather a declarative approach or a non-functional approach may be clearer or a better way to solve problems or the way that people really think. And there's some contention back and forth. What I can tell you is that Python is a tool that is very amenable to writing programs in a functional style. It makes it very easy. In the same sense, when we talk about generators, Python isn't the best language in the world for writing code that follows this coroutine style. There may be better languages out there like Scheme or some Lisp dialects, who knows. But Python allows us to write this code in a very easy way. It's amenable to it. It's a very convenient way to write it, with a couple of small caveats. So I told you I wouldn't tell you what a generator or coroutine is. I lied. I'll tell you very briefly. This is a function, and you'll see this function all over the place. It's just a Fibonacci sequence. I'm sure we've all sat in an interview somewhere, and somebody's asked us to code this out. It doesn't do anything particularly interesting. You give it 2 initial values, and you give it an n, and it gives you the first 10 Fibonacci numbers, right? Nothing too fancy here. And here's another function I wrote. And I put these notes together very quickly, so these functions aren't even written very well. And it's called ratio, and you give it a sequence of numbers, and it'll give you the ratio between subsequent terms. The reason I wanted to bring this up was I wanted to show you something kind of cool about the Fibonacci sequence, which is if you look at the ratio, and you take phi, and you'll see that the ratio of subsequent terms in the Fibonacci sequence converges to phi, which isn't terribly useful to know. However, phi is very close to the conversion between kilometers and miles, right? So if you ever find yourself overseas where somebody gives you a distance in kilometers, you can actually convert it very quickly to in your head into miles if you know terms of the Fibonacci sequence, because adjacent terms will give you that conversion. In other words, about 2 kilometers is 1 mile, about 3 kilometers is 2 miles, about 5 kilometers is 3 miles, and so forth and so on. So I thought that was fairly useful, although I've never actually found a real-world use for it. So who knows? Back to the function. Here it is written as a generator. This is a very, very simple generator. If you go to the Python subreddit, you'll even see that they have this in the sidebar. And you can see a couple of notable things. Instead of a return, I have a yield. You can see it's a lot shorter. And you can see that when I want to get out the same values, the first 10 values, you can see that instead of encoding that into the Fibonacci function itself, I now have externalized it. It is now the user's responsibility to tell me which values he wants. And he does that using a very nice function from itertools called iSlice. He gets the slice of the first 10 elements. And what this shows us, and then here's also our ratio function. And you can see our ratio function actually turns out to be very, very easy to write by composing things from itertools. So I first created nys. I use this all the time. Seriously, every problem in my life can be simplified down to nys. Like I'm at home on Friday night and I'm really lonely, and I'll use nys to find a date. It's nuts. Every problem has some application for nys. Ratio as well. You just get the initial sequence and you split it into windows of 2 numbers, and then you take the ratio of the numbers. Pretty straightforward. Oops. However, what I want to show you is how this generator encoding of the same problem can free you from certain presumptions, like presuming how the function will be used. In our first case, I gave this n parameter to get the first n Fibonacci numbers, right? But somebody could argue, well, I don't want the first n numbers. I want the first numbers that aren't larger than n. So instead of the first 10, I want the first numbers that don't get larger than 10. And you can see I've written 2 different functions here. Imagine what it would look like if I had to implement both of these in the same function, and how many switches I would have, and how complicated it would be to read. Whereas in the generator formulation, the function itself doesn't change. The responsibility for how to use these values is left to the person who wants to use these values. And they'll use tools like iSlice and itertools or takewhile and itertools to get the first n values, or to get the values not larger than n, or any complex predicate that they want. So in the last example, they want all the values where the values are larger than 5 and smaller than 100, and no more than 15 values in total, right? So you could do any complex predicate. And imagine how impossible it would be to encode this very complex requirement on the return values in the Fibonacci function itself. Additionally, we've freed ourselves from a presumption about what parts of the return value somebody wants to use. So let's assume that there's some function in our system called query. And it may be a database query, or maybe a large computation. And I put a sleep in there just to simulate that this is a very expensive computation. And you could think that if it were the Fibonacci function, and you had a little sleep in there for each number that you generated, then you'd have 10 sleeps in a row before you could return a value. Whereas in the generator implementation, in the generator encoding, you only need to incur the computation that you need in order to get the values that you want to use. So I'll give you a very real-world example of this. I was once dealing with a large trading system. In the trading system, they had a function that would give you all the trades in a portfolio. So it would say, you know, this is a portfolio that trades distressed loans, and here are all the distressed loan trades that we've done today. And it was a trading desk that did a lot of trades, like millions of trades. And when I typed get all trades, what the function would do is it would go to the database and would pull the trades and return them to me in a list. Except that list was so big, I'd run out of memory every single time. And I only wanted the trades that matched a very specific signature. I only wanted the trades that matched a specific type, because I was only looking at a certain number of cancel trades, right? Except the person who wrote that function wanted to return everything to me, presuming that I could just use that and filter down from there. But you can see I didn't want all the trades. I don't want 1 million return values. I want to get return values one at a time, and as I see them, pick which ones I want to keep. If this had been written as a generator, in a generator form, you can immediately see that I no longer have to presume what you want of the data. You get to choose which pieces you want, which pieces you want to keep. And you don't have to incur computations that you don't need. In this case, you don't have to incur a computation beyond the first computation, because you don't care about any value but the first. Additionally, generators can free you from certain presumptions about the return type. So you could think that we've all written functions, and we could never really figure out, should this return a list? Should it return a set? Should it return a tuple? Should it return a deck? Who knows what it should return, right? And you have to sit down and think, which of these do I want to choose? And I feel that whenever you're in a situation where you need to make a choice between one thing and another thing, there's almost always some reason to pick one path and not the other. And in cases where it doesn't seem like there's a particularly good reason to pick one path or the other, there may be the choice to pick neither path. And generators, in this case, free you from making a choice at all. Here we have 3 functions and they all return different values. And it may not be clear which of the ones that we want. If this were written as a generator, you could think that we wouldn't even have to choose which return value we want. We'd just write process, it would yield values out, and the caller would be able to determine where he wants to put them. And so for an example, we'll take our same Fibonacci function, and you can see here it returns a list. And you can see this is how long it takes to run it 100,000 loops. And if I ended up wanting a tuple for some reason, or maybe I want it to be immutable, or if I wanted a set for some reason, I'd have to do a cast, or I'd have to do a construction of a set or a tuple. You can see there's some time and some memory that's incurred. Whereas in my generator formulation, you can see not only is my code simpler, not only do I no longer have to presume what kind of return type is going to be best suited to your purpose, but it's actually on par with as fast. Now, I'll tell you that all benchmarks and all presentations you'll ever see are all BS. And this one in particular, because I had to run this like 4 or 5 times before I can get the numbers to look right. But you can see they're within the same range. They're within the same range, and for the set, it's actually faster to just return the values. I can tell you, in one sense, the generator formulation is strictly better, which is if this were a large result set, you need to have both result sets in memory at the same time, the one in the data type you wanted to have and the one in the data type it returned. Whereas in the generator formulation, you only need to have a result set for the data type that you want. You wouldn't have to maintain both sets at memory at the same time. Additionally, I'll show you that we commonly see this problem, but from another angle. Namely, we commonly run into code where somebody's made a presumption about the input type, not the output type. And we've banged our head against the wall about all these presumptions about input type. So here's an example of a function. It's called average. And you can see somebody put in an isInstance list. And so this will only ever work against lists. And so I do an average of the first 5 powers of 2. And you can see if I switch this from a list to a tuple, it gives me a type error, and it says XS must strictly be a list. Now, I'll tell you one thing that I couldn't figure out. Should it be XS strictly must be a list, or XS must strictly be a list, or XS must be a strict list? That's one thing for you to figure out later. I don't know which one was better. But you could think, why do I care that it's a list? I'm just going to iterate over it. I should reduce the presumption that I have about how this function is going to be used and allow you to give any iterable. So somebody will come in and they'll say, well, actually, let's use sized from collections. And here, and we need size because we're doing a len here, and sized is anything that returns a value when you call length or responds to length. And now you can see it works on a tuple. And then somebody will say, well, you're taking the average, so you don't really need to have a len function. You could just write this. And here, I don't have any presumption whatsoever other than it's something that can be iterated over. And we might argue that this is strictly better code than the first one. You can give me anything that I can iterate over, and I'll give you the average of it. So you can give me a generator. You can give me, in this case, you can give a generator expression. You can give a list. You can give a tuple. Any of them will work. And so it's more robust in the sense that changes in input value won't cause this function to, or the input type won't cause this function to fail. And it's more accepting of different inputs. Generators also can simplify your APIs and remove some of these presumptions about mode. So I want to go in depth into a couple of examples, I think 2 or 3 examples, to show you how we can change the way we think about our code, and as a consequence, simplify APIs and remove a lot of presumptions, a lot of weird encoded modalities that we have. So the very first example is for a little bit of processing. So here we have just a simulated version of some data processing function, right? And you can see load data is the function that loads some data. This is for loading data from some resource. So you can see load data will load data from some resource, and that source it could be a database, it could be some large processing chain, it could be anything. And I've modeled it by just having a little generator there that sleeps, just to show that it's a time-consuming process. Maybe each query from the database takes some network round-trip time. And you can see that it takes a little bit of time to run to the end. And on the slides, you can't see it, but on the actual IPython notebook, it's kind of neat when you see the next slide. And somebody comes to you and they say, well, it really bugs me that I can't figure out where this is in the process. So why don't you add a little counter to it? And I'll show you the counter actually a little works, and it's kind of cute. It's kind of lame too, but no, it's awesome. It's the best thing ever. I shouldn't, yeah. So I'll show you. Here's the example here, and you can see, oh, look, isn't that nice? So you can see kind of where it is in the computation. And then somebody says, well, I want to see when it starts and when it ends, because I want to have this little message that says it's done loading, right? And you can see all of these different things that we've encoded into this. We have a print loading, a statement at each step, and a statement at the end saying it's done. And you can see if you go to here, you'll see the same thing. Isn't that nice? And you might have seen this talk and at least seen the first few minutes of it before you dozed off. And you might say, there's a better way to do this. Let's use functional programming. So instead of encoding these directly into the function, we'll provide a before, a during, and an after function, right? So we have something that gets called before, something that gets called during, and something that gets called after. And you can see we end up with the same thing. We end up with a nice little guy here, and it just prints. But it turns out there's a bug here, because I accidentally swapped the before and the after. So it printed done loading before it printed loading. And you can think that I've actually allowed the user, I've provided them with an API where I said, here's some functions, and you just call them whenever you want, right? And I've actually allowed the user to make this problem. It's partially my fault. In a generator formulation for this, instead of providing 3 functions, I'll provide one function called update that can no longer be misused in this fashion. The before, the during, and the after can only be called strictly in a set order. You can't call the after before you call the during. You can't call the before after you call the, well, you can always call it before. You have to call the before first, and so forth and so on. And you can see in this case, I've simplified the API dramatically. This update is just a generator itself that just takes a value and yields some statement, some loading, and then some percentage, and then some done loading. And you can't, it's much harder to misuse because there's not much you can do with this other than what's being done here. And you can see in the load data itself, all we do is for each data that we process, we just iterate through this generator to print out these messages. So we end up with exactly the same functionality. We end up with a little bit more flexible functionality because we could encode anything in here. We could encode any sort of loading message. We could have splash screens. And we've also simplified the API in that it's a little bit harder to misuse. We couldn't run into the same problem we had before, where I just had 3 functions floating around with no structure implied. This generator formulation actually implies a structure in terms of sequencing. So I want to go into an in-depth example. And to start, I wanted to show you, if you go to SIFMA, they are one of the regulatory agencies for fixed income markets in the US. They have a holiday calendar, and they have a list of all of the holidays, all the bank closed holidays in Japan. And there's a lot of them. I mean, look at that. And they take off holidays we don't even take off. They take off Thanksgiving. Their banks close on Thanksgiving, and our banks don't even close. Well, actually, they do. They take off Respect for the Aged Day, which I don't think we have. They don't take off the Queen's Diamond Jubilee, thankfully. They do take off Children's Day, which I wish I could get, and National Foundation Day. It's ridiculous. And you might actually see code like this in terms of calculating business dates. And this is something that every business has. They need to calculate what's the next business day for running any of their reports, for running their P&L reports, their position reports. They need to figure out what the next business day is. And here I have a very simple formulation for this. It's called nth business date. You give it a starting date. You give it how many dates out you want. And I've even shown you a calendar with the holidays marked. The 4th of July, they take off the 4th of July. And the 21st of July. And I have to figure out what the 21st of July is. I don't even know there's a holiday there. That would be Marine Day. There you go. And you can see nth business date, given the 2nd of July, and wanting to go ahead too, it'll go to Thursday, then it'll skip Friday, Saturday, Sunday, and hit you on Monday. So it'll go from the 2nd to the 7th. And you can think that maybe for some reason I want to generate the next 3 business days, because I want to run a report to compare them, or I want to look at my position over time, or I want to look at my P&L over time over these 3 days. And you can think that each time I call this function, it's going through this while loop, starting from the same ref date over and over and over again. So I'm actually doing a little bit of redundant processing. I'm counting up, and I'm counting through each of these weekdays and each of these holidays over and over again. And it may not be a lot of redundant processing, but if there were a database call to pull this calendar out of a database, I'd be incurring that 3 times. So you might immediately say, this is more amenable to encoding as a generator. And here, I just have a function called business days that gives you an infinite sequence of business days, starting from some point. And you can see I started from that, and then I have my holiday calendar, and it just yields out business days. And now if you want the next 3 business days, you use next, or you could use islice to get them out. And we no longer have this redundant processing, because this generator, or this generator will exist in memory as a frame object with a code object, and all the resources that it uses will persist until there are no more references to the generator. And each time you yield a value out of that, you're just going to get the next element in the sequence. You're not going to have to start the computation over from the beginning. However, you could think that if I have business days and I want to look at the next business days, I might want to look at the previous business days as well. One big theme of this talk, I think, is that every time you write a piece of code, it'll grow. People are going to ask for more things out of it or more functionality. And the advantages by encoding functions in one way or the other, by writing functions or using functional programming or using generators, is to allow yourself to work more effectively with some of the changing requirements for the code that you write, or at least to free yourself from having to do more work when the requirements change. So in this case, somebody's asked to do business days going forward or backwards. And we have next business day and previous business day. And you can see what we did was, instead of adding one date, we use a function. And that function is just addition or subtraction. And so you just pass in this parameter if you want to add one day or subtract one day. Otherwise, the code's the same. But if we really think about this, we could break this up even further. And you could think that what we could do is we could write a function called dateCount. And it's similar to itertools.count. And all it does is give us an infinite sequence of dates starting from a fixed date. Count in itertools, you give it a number, and it'll just give you from that number to infinity. And this dateCount will just give you some number to infinity in one direction or the other. And you could see, instead of encoding this as an add or a subtract, I've actually encoded the stepping. So this could give you, just like range gives you from some start to some stop on some step, this could give you from some start, and the stop and the step are actually encoded in this direction parameter. So you could step by 2 days or step by 3 days as you desire. And then I can write business days very simply. Look how short this is compared to before. Yeah. This one would handle February 29 as a, well, it'll just work because the +1, because it's using Python's internal datetime arithmetic, which will handle leap years by itself. But let me show you a couple more things, because it gets wilder from here. We can see that the business day function is now much simpler. Instead of this embedded while loop inside this while loop, now I'm just returning all the days starting from some point if the day is not a weekday and it's not in my list of holidays. So I've actually simplified my code quite a bit. And you can see if I want to get the next business days, I can get them, and I don't have to incur. I can get them forwards, I can get them backwards. And the actual use of this has remained unchanged. And you could think that if I wanted to, if these were coming from some database or there was some delay in being able to pull in the dates, I could encode this to a higher degree of sophistication by modeling two generators consuming each other. So what I've done is I've taken the same business days, and instead of holidays just being a list that I check not in, where this API is a little bit richer, right? I need to have some object that responds to contains. Say I don't want it to respond to contains, which is a much richer API than having it just respond to call. So now holidays is just some function that responds to call and gives true or false. And it just happens to be a generator in itself that just picks up holidays, and it'll tell you if that next holiday, if the date that you're sending to it is a holiday, and if not, it will, if it is the next upcoming holiday, it'll return false. If it isn't the next if it is the next upcoming holiday, it'll return true, otherwise it'll return false. And what I've done here is I've also encoded just a simulation of having to look this up in a database. So you can see I have a calendar, and it sleeps for 2 seconds each time we try and pull a holiday out. And you can see here what it'll do is when you pull in the dates, it'll advance to the next holiday, and it'll just keep that next holiday in memory until you ask it for a date that's past it, then it'll advance to that. Well, what this results in is this first call to figure out the next 3 dates takes 3 seconds, because we have to go from the beginning of the calendar up till July and figure out all the holidays and incur all of these sleeps up to there. But every subsequent call using the same generator object only incurs the cost of getting the next holiday item. And you could think that if your cost for opening a database connection were greater than your cost for querying a record, but the querying a record cost was still great enough that you didn't want to query everything, this is actually a much better formulation because you're reducing the amount of computation that you need to do to get the values you want. So here's my last example. And it's about counting change. And I think we've all run into this question in some interview circumstance somewhere. Somebody asks you, how do you count change? And so here, I want to count change from $1.72, and I want to get it out. I want to see what the coinage is that would be returned. And I have to apologize. This slide I put together in a rush, and you'll see there's this nasty stuff about decimal because 0.01, the conversion of that into floating point was not working with this. I was getting rounding errors, so I had to use decimal so I could get full precision. So I apologize for some of the complexity added to that. But you can see this is a pretty simple little piece of code. We loop while there's any denomination that we could pick. If there is a denomination, we pick that denomination, we add it to our list of coins and return. So for $1.72, we get $1, 50 cents, two dimes, and 2 pennies. But somebody comes to us and says, we want to make this a little bit deeper. Like, we don't have an infinite set of change. We have a fixed number of coins. So I want you to encode that in the problem. And here I've added to this, and I've said, instead of just checking if there's a denomination that fits, you also have to check if there are any of them left. And so instead of giving a list of denominations, I have a dictionary of them that maps the denomination to the number of coins you have left in your change drawer. And so now I can figure out how can I make change for $1.72 if I have a finite number of coins. And you can see if I change the number of denominations, I have only three half dollars and 10 dimes and 20 pennies, the result will change. See, I don't have any dollar bills here, and I have a limited number of coins. And this may actually model a real-world circumstance. And you can see again, if I change it so that I have a lot of dimes, a lot of pennies, it'll change even further. However, if we wanted to really free our minds and change the way that we model this fundamentally, we'll reach for iter tools, and we'll think, what is this process of counting change? Well, we have some sequence of things, and we want to pick from them until some predicate tells us to stop. And we can build that from iter tools very easily, namely this. And that's all it is. The chain from iterable is merely a mechanism because what we get is a list of lists, and we want a flat list. And it's actually not terribly, we could have encoded this with a generator expression and done 4x and y for y and z if we wanted. But this is really the meat of it. Namely, we have some change drawer of denominations called x. We have an infinite sequence. We want to take from that until some predicate tells us to stop. And we can encode that predicate fairly easily. And it just looks like this. It's just a coroutine. And what it does is it takes values until it can no longer take them. And there's some interesting things about this coroutine, which is it doesn't change the value of the thing you're looking for. In the previous example, you can see that we have to mutate the amount in each step. Here, we're not actually mutating the amount. We're counting up. And you can see that it's a little bit more complicated, but it gets the same job done. Until, and here's an example of it being used. So you can see we randomly pick dollar amounts, and we can calculate the change, and I've printed it out for you very nicely. And this all works very nicely until somebody tells us, well, we want to do this, we want to add a little bit more functionality to this. We have limitations. We want to make sure that you only have a certain number of coins. And you can do that very easily. In your predicate, you just add a constraint. And the constraint says, based on the values you've already picked and the value you're about to pick, can you move forward? And in the case of a fixed number of coins, you can see, I should have called that 2 coins. You can see we can encode that just as easily. The actual body of the code we've written hasn't changed. The predicate just takes one more argument. And that constraint is the number of coins you can have for any one grouping can be no greater than 2. But you can think here we can do some very interesting, very complicated predicates here without having to change that original library code. Namely, if somebody told us you can only have 2 dimes if you have a nickel, otherwise it has to be all quarters and pennies, how would you write that in this original formulation? How much additional code would you have to write to encode a complex predicate saying you can only have an equal number of coins that end in the same digit? And how much would you have to change this to get that to work? And could you even encode all the different things that somebody wanted or somebody might ever potentially want? Whereas in the generator formulation, by freeing yourself from certain presumptions, and by modeling the code in a fundamentally different way, by thinking of it in terms of just some sequence and some predicate that operates on the selection of values from that sequence, we can now encode any complex predicate that we want. This predicate that we send it, this constraint that we send it, could say anything we want. And we wouldn't have to change the original function. We wouldn't have to change greedy. We wouldn't have to change predicate. It would all be controllable from the outside. This is how generators can free your mind. But I want to show you one more interesting thing. Without changing any of the code whatsoever and only changing the inputs, I can now fundamentally solve a totally different problem. All of the code here is the exact same as before, except the printing is a little bit different. But you can see the same thing, the same greedy algorithm, the same predicate. And you can see now I can do conversions from Roman numerals to Gregorian, to Arabic numerals, using the exact same code that I used to count change. Because fundamentally, they're the exact same process. It's just a greedy algorithm picking elements. And I can apply the exact same predicates and the exact same constraints I want to this. So I think this example should show you how, by fundamentally changing the way that you think about your code, you can not only free yourself from presumptions about how people are going to use it, make your users happier, empower your users, and also allow for certain formulations that would be impossible or unwieldy in the typical way to write your code. So I'm happy to say that I hope for some of you, generators have freed your mind. Please go in peace. My name is James Powell. I think we have time for a couple questions or lunch.
First of all,
sorry, so 1 second. So people filter out if you need to. We'll get back to the question in a second. I have 2 announcements before you go, just in case people need to leave early. Lunch is through that door. Don't go through that door. Go through that way. Yeah, so just follow. There's people walking over there. Second announcement is that Alex Bokov, his talk it's on the schedule. There's a typo. It said that, so it's the next talk after this one. It said he's going to be in Sung of Ping and Pong, but he's actually right here. So everything in this column is in this room. So those are 2 announcements. Lunch that way. Small typo. Back to the question.
So first of all, thank you very much, because I wanted to give a talk about generators myself, but never got around it.
So I was on the proposal selection committee, so I would have nuked your talk and picked mine. Just saying.
I didn't have it ready, but thank you. Because I think a lot of the people don't use generators because they're not taught in schools, and other languages, they don't have it the same easy way to use them as in Python. But my question is, you had a decorator called pumped, I think?
Yes.
What does that do?
So I told you at the very beginning that Python isn't a theoretical language. It's not the best language for thinking about things in terms of generators. It's merely a language that offers you a practical way to encode your problems using this tool. And one of the warts that you have in Python is the need for this decorator called pumped. Now you'll see it in every single library that uses coroutines. It'll be called pumped, it'll be called primed, it'll be called coroutine. And namely, there's a little syntactical weirdness when you have a coroutine. Namely, you can't send values to it until you've started it. And there's this really obscure error message that says can't send none values to a just started generator. And all this guy does is take it out of the way. It actually does one more thing that I particularly like, which is it turns the, it's actually not in the slides. It's here. I hid it because I didn't want to show you. It's really ugly. It's really unpleasantly ugly. So here it is. Pumped is up here somewhere. Yeah, here it is. What it'll also do is it'll turn the generator into a function, so it'll just return the .send method, so that the API that you get from your generator is just calling, not iterating over it. And it allows you to simplify your API somewhat. Any other questions? No?
So another little wart that I guess you've run into is the somewhat awkward syntax where you have to emit a value and receive a value in the same yield statement. I've written another decorator which separates those into 2 separate steps. So if you're at all interested in that, come and find me at some point, and I'll be happy to show it to you.
Yeah, it's a unpleasant and uncommon problem that I think we all run into when we start doing anything 2 series with generators.
Maybe one more quick question. Anybody? Quick one?
Whose mind has been changed about the use of generators? Nobody?
Yeah.
Who's going to go into their code base tonight and replace every function with a generator and completely upset?
Please, God, no.
And you can blame me. You can
Please,
blame me.
no.
You'll find me on.
Don't use this code.
Yeah.
Let's give a hand for James.
Thank you.
Wizardry.